All right, so let's talk about finite infusions, or what I call start-stop infusions. Essentially, this means I know when my infusion is going to begin, I know how long it's supposed to take, and my patient's going to get the entire amount. And so what we can do with these is we need to be able to determine an IV flow rate or infusion rate. Those are the couple words that you'll hear or see when you hear these talked about. And so basically, I need to be able to program my pump to run at the rate it needs to run in order to get this infusion complete in a certain amount of time. I can also use a drop chamber or micro drop or macro drop tubing. And you've probably talked a little bit about this, but when we get into that, I'll also explain further what those tubings mean for your calculations. So let's talk about milliliters per hour first. This is the very standard way to program IV pumps. Essentially, you're telling the IV pump how many milliliters, so liquid volume of this solution, to put through in 1 hour. So that's what this means. So what I'm going to do is I'm going to take the total amount I'm supposed to give, total milliliters, divided by the total time it's supposed to take, total hours. That will give me a milliliter per hour rate. Now this should sound familiar to you from when we talked about urine output and calculating how many milliliters of urine someone's been averaging every hour. We did the same thing. We talked about what's the total amount they outputted, how long did it take for them to do that, and so then we can see what the average is. So this will give us a rate for that. So let's take a look at a problem and see what that's like. Okay. Your client needs 275 milliliters of normal saline prior to going to surgery. The client's going to leave for the procedure in 3 hours. So how fast do you need to run the infusion in order to get it done in time? Here we see that we have a total amount of milliliters that we're supposed to give. It's supposed to take 3 hours. It has a start and a stop time. So when I take my total amount of milliliters divided by my total time, so 275 milliliters divided by 3 hours, then I get 91.666 repeating. And so that we are going to round to 92 milliliters per hour. Now, this is going to be one of your standard Mercy rounding rules, also applies to your HESI exam. Whenever I do a milliliter per hour equation, I'm going to round to a whole number. The easiest way to remember why this is that this is what your pump understands. We often cannot input decimals into our IV pumps, so whenever we're doing a milliliter per hour, we're going to round it off to a whole number. The pump doesn't understand how to give a partial milliliter. It's either all or nothing. So it's either going to give a milliliter or it's not. So there's no room for decimal places. Unless you're working in a very critical setting like the ICU, your standard pumps are not going to be able to take that kind of information. So we round it off to a whole number. So another way we can administer a finite infusion is to do drop tubing. Now, you guys have probably already started talking about this, but I just want to review some really important information for calculating an IV infusion. First of all, instead of a milliliter per hour rate, our rate is going to be in drops per minute. So when you think of your little chamber and the solution dropping into that chamber, we're talking about how many drops should this tubing drop every minute in order to give the solution in the amount of time that the order says it needs to be given in. So this is going to be equal to the total milliliters times the drop factor of your tubing, all divided by your time, your total time in minutes. So just look at a couple of clues here. When we're talking about milliliters per hour, our time should be in hours because our label is hours, milliliters per hour. Here, our time should always be in minutes when we plug it into our equation because our label is drops per minute. This is the same equation you're going to use for every single drops problem that you have. So refresh your memory. There's different types of drop tubing. We have micro drop tubing and macro drop tubing, and what this means is little versus big drop. So a little drop is referring to micro, and macro means a big drop. Micro is always the same drop factor no matter what. And what's drop factor? Drop factor is how many drops from this tube does it take to equal 1 milliliter. So for micro, our drop factor is always 60. If it's micro drop tubing, you can always assume it's going to take 60 drops to equal 1 milliliter using this tubing. For macro drop, it can be variable. Macro means big drop. And this type of tubing, you're just going to have to know from the problem or from the package how many drops is equal to 1 milliliter. It could be 40, it could be 20, it could be 15. So it's always going to need to be told to you what the size of the drop is. And that's how many drops is equal to 1 milliliter. Then when we think about that total time, again, we always need it to be in minutes. So think about, how do I convert from hours to minutes? So if my problem tells me I have a solution that needs to be given in 2 hours, how do I convert that over to minutes? 2 hours, we take times 60 to go from hours to minutes. So just make sure you do that conversion before you move on with your problem. So let's take a look at an example here. Just a minute here. Okay. So let's look at the same example we just did with the milliliters per hour, only now let's pretend we have drop tubing. So our client needs 275 milliliters of normal saline prior to a scheduled surgery. We've got micro drop tubing available, so let's stop right there. What does that mean? How many drops per milliliter am I working with? What's my drop factor? 60, right? If it says micro drop, I can just assume that. And so sometimes your problems will tell you GTT drop, micro GTT. Again, GTT just stands for drop, so that just means small drop. The client will be leaving in 3 hours. How many drops per minute should we administer to get the infusion completed in time? Every time I do a drops equation, I use this drops problem, I use the same equation, so I'm just going to pull that out verbatim. Drops per minute will always be equal to my total milliliters times my drop factor divided by my time in minutes. So for this problem, I'm going to give 275 milliliters of normal saline, and it's going to be using micro drop tubing, so I know my drop factor is that 60 drops is equal to 1 milliliter. So I've got 275 times 60 on the top, and I'm going to divide it by my time in minutes. Now I said that I just take my hours times 60 to convert over to minutes. So 3 times 60 is equal to 360 minutes. So in this case, when I complete the problem, I'm going to get 45.83 repeating. Just like we did for milliliters per hour, we're going to round this to a whole number. So these are the 2 instances in which you are going to be rounding to a whole number. Otherwise, it's always going to be to the 10th. If it's greater than 1, or to the 100th, if it's less than 1, always to the 10th on a weight. But for milliliters per hour, I'm programming a pump. It only understands no milliliters or 1 milliliter, so I'm going to round to a whole number. In this case, when I'm looking at my chamber and my tubing can only drop 0 drops or 1 drop. It can't ever drop a partial drop. So it's always going to be rounded to a whole number again. So this 45.83 repeating will be rounded to 46 drops per minute. That's how fast I need to have my chamber drops every minute in order to get this full amount of solution in 3 hours prior to my client leaving. So let's look at another example here. It can look a little bit different the way that the wording is in the problem, so I want you to be prepared. Your client needs to receive 20 milliequivalents of potassium in 1,000 milliliters of normal saline at a rate of 150 milliliters per hour. You have tubing with a drop factor of 20 drops per milliliter available. At what rate in drops per minute will you administer this IV infusion? So I hear that it's talking about drop tubing, so I already know I have to use the drops per minute formula in order to solve this. So I'm always going to use that drops per minute is equal to milliliters times drop factor divided by my total time in minutes. Now, drops per minute is always used to do a finite solution, a finite equation that we're talking about right now. So I know the total amount that my patient's going to get. It's that 1,000 milliliters. Don't get hung up on the 20 milliequivalents of potassium. Yes, there's 20 milliequivalents of potassium in that bag, but because I know my patient's getting all of it over a set amount of time, I don't have to worry about how many milliequivalents is in each milliliter and all of that, because they're just getting the whole thing. So really the potassium part of it, because it's a finite solution, because it's a start-stop, I can ignore for this time. I know that it's supposed to run at a rate of 150 milliliters per hour. So don't get confused that just because it talks about milliliters per hour, we're still going to be using a drops per minute equation because our question is asking us for the rate in drops per minute. And then I know that my drop factor is 20 drops per milliliter. So that means that I'm using micro or macro tubing. Macro. Yep, I'm going to be using macro drop tubing. So let's try to fill this in. How many total milliliters of solution am I going to be giving? At first glance, it really looks like 1,000 milliliters. In fact, that is the total amount of solution that I'm going to be giving. But do you know how long that's supposed to take? We don't. There's no association of that 1,000 milliliters to time. And in order to do the drops per minute equation, we have to have an element of time. So when you look at this question again, what part of it tells you how much time the solution in some capacity is supposed to take? The one place I see time here is that 150 milliliters per hour. That's an amount of solution in an amount of time. So even though it's not talking about my total solution, I can still use that piece because it gives me a reference. It tells me that 150 milliliters of this solution is supposed to take 1 hour. So that's what I can use. So if I plug that in, I'm going to use a total milliliters of 150. Again, I'm just going to plug in my drop factor, which in this case is 20 drops per milliliter. And then my time in this case is going to be 1 hour. Now remember, it has to be in minutes, so 1 hour times 60 or is equal to 60 minutes. So that's the time that I'm going to put in. So in this case, I just use that rate. So it sometimes can look a little bit different, but you're always going to pull out the amount of milliliters that's associated with an amount of time in order to solve. When we do this, 150 times 20 divided by 60, we're going to get a drops per minute rate of 50. So I'll just put that down here so that you guys can see it. I don't have to round on this because it came out to an even number, but I'm going to see 50 drops per minute from that chamber, and then it will go at the rate it's been ordered at for 150 milliliters. So there is one more thing I wanted to point out to you with drops per minute equations and drop tubing. Your client needs an infusion of vancomycin. The infusion is available in 250 milliliters. It's supposed to be administered at a rate of 50 milliliters per hour. We've got micro drop tubing available. So everybody answer, what's my drop factor for micro drop tubing? 60 drops per milliliter, forever and always. And so at what rate will my infusion run in drops per minute? Always going to use my drops per minute equation. Drops per minute is equal to the amount of milliliters I want to give times the drop factor of tubing I'm using, all over the amount of time that's supposed to take for those milliliters. So in this case, again, I can fill in my equation, 50 milliliters times my drop factor tubing of 60 over my time in 60 minutes, because it's supposed to be 50 milliliters in 1 hour. So I've converted that 1 hour over to 60 minutes in order for this equation. As you can see here, I've got a 60 on the top and a 60 on the bottom, and anything that I have on the top of my numerator as well as the bottom of my numerator is going to cancel out every time. So in this case, my 60 here cancels out, my 60 here cancels out. I'm only left with 50. Forever and always, if you are using micro drop tubing and only micro drop tubing, because my drop factor is 60, when I have my milliliter per hour rate, it will always equal my drops per minute rate. So in this case, we can see that my drops per minute is going to be 50. I'm using micro drop tubing, so that will always be equal to my milliliter per hour rate. So if you want to remember that shortcut, you definitely can use it in the future. It's always going to be true for micro drop tubing. However, if you would rather just write it out every time, that's completely fine. Obviously, if I took 50 times 60 and divided it by 60, I'm still going to get the correct answer of 50 drops per minute.